Okay guys, welcome back. So I took the liberty of erasing some things and writing a few things down that weren't there before. So last time we basically set up the framework that allowed us to start deriving this mean value analysis algorithm. So we had this closed network over here, and remember we had these p-values. So what are those p-values? Well, p1, p2, p3. pi is going to be the probability that given a job arrives to a node, it arrives to node I. So I'm conditioning, okay, there's a job, it's arriving to some node. What's the probability that's going to arrive to node I? That's pi. You can think of these as probabilities or proportions, right? What's the proportion of jobs that arrive to node I? Well, that's going to be the probability that given a job arrives somewhere, it arrives to node I. I've also written down a few pieces of notation here. So look, I have this, kind of to the power n, but in brackets. So this doesn't mean ri to the power n. It's just like a superscript n. It's just denoting another piece of information. So what's this? Well, this is the expected response time of node I given that there's exactly n jobs in the system. Likewise down here, this is going to denote the expected number of jobs at node I, with the subscript I, given that there's exactly n jobs in the system. Okay, what's this last one? Lambda, kind of superscript n. It's not lambda to the power n. It's just a denotation. Notation thing. So this is the total rate of arrivals when there's exactly n jobs in the system. So if I were to view the system, maybe n equals 3. There's 3 jobs in the system circulating, right? And I have like a counter over here. Every time I see a job arrive to any node, I click the counter. Okay, arrive to that one, click. Arrive to this node, click. And I do that for a very long time, infinity theoretically. Take the total number of counts, divide by time. That's going to be the arrival rate or total arrival rate in the closed network. Okay, before I get to the mean value analysis, I need one more thing. I know I keep saying I'm going to do it, and I was like, oh yeah, you need one more result, you need one more theorem. Oh, don't forget this notation. Yeah, that's math. That's theory, right? That's the world we live in. So what about this? Lambda in. Well, this is going to be the arrival rate to the ith node when there's n jobs in the system. And what's that going to equal? Okay, well, assume I know this. Assume I know the total arrival rate. If I know the total arrival rate, I know the arrival rate when there's n jobs in the system. What's going to be the arrival rate to the ith node when there's n jobs in the system? Think about that. Well, for instance, if I know 50% of the arrivals occur to the first node, I could say that, well, lambda in, that's going to be 50% times the total arrival rate. And you can use that logic throughout, and what we find is this equals pi times the total arrival rate. So if we know the total arrival rate to the system, and we know pi, we can solve the pi's from the network. Then we can solve the individual arrival rates. Okay, so what's the goal here? What's the point of the mean value analysis? Well, let's draw a block off here. We want to find the expected value of r at n, for I, given we have the previous value, or decrease n by 1. So if we know the expected response time of the node, if there's n minus 1 jobs circulating through the system, we want to be able to calculate what if there's n jobs circulating through the system. Okay, so in essence, we want to build a recursion for the expected response time at a given node. Okay, well, before we write out this recursion, what else do we need? Well, if we want a recursion, we need a recursive step, and we need a base case. What's going to be our base case here? Well, what if I take the expectation of the ith node? You might think, well, let n equal 0. Maybe we could do that. Maybe you could have a philosophical discussion. Well, what's the expected response time of node I if there's 0 jobs circulating through the system? I mean, that's kind of weird to think about, right? There's no jobs in the system, so it doesn't really have a response time. Maybe you could think it's 0. That might be a reasonable conclusion. But let's avoid that, intellectual gray area, and let's just see if we can solve. Well, what if there's one job circulating through the system? Okay, well, if there's exactly one job circulating through the system, maybe it comes down here. Whenever it arrives to a node, how many jobs are going to be ahead of it? How many jobs are going to have to be processed before it gets served? Well, I mean, think about that. It's the only job in the system. If I'm checking out at the grocery store, assuming the grocery stores are open, right? I get to the checkout. If I'm the only customer in the store, there's going to be no one ahead of me. Okay. Well, if there's no one ahead of me, my response time just becomes my service time. Well, that means this equals 1 over mu I. Remember, mu I is the processing rate of the ith node. So that's our base case. Well, if that's our base case, let's try to write out our recursive step. Okay, so that's the base case. What about for a general n? This one's harder. I mean, what exactly would you have to figure out? Well, think of it this way. When I arrive to a queue, what's my response time going to be? Well, it's going to be my service time plus the time that's going to take to process everyone else. Well, that's the tricky part. I know I at least have the service time. I know 1 over mu, but how long is it going to take to process everyone else? Well, how might I start to grasp that? Well, there's a key piece of information. When I arrive to a job, when a job arrives to a node, how does it view that node? What kind of steady state does it view it in? Remember this. So when a job arrives to a node, it sees the entire system in steady state with 1 fewer job. Well, if it sees the entire system in steady state, it certainly sees the node it just arrived to in steady state as well. So how many jobs are going to be ahead of it? Well, it's going to be, or it should expect to see ahead of it. It's going to be the expected number of jobs given that there's 1 fewer job circulating through the network. Okay, so I have my service time, mu I, plus the expected number of jobs at node I. Okay, cool. With n minus 1 jobs circulating. And for each of those jobs, I'm going to have to expect, or have to wait for it to complete its service time. So I'm going to times that by 1 over mu, or I can just divide this by mu I. Okay, well that's something, but it's not like I get free access to this. It's not like I know that for free, but I can rewrite that as something else, right? Remember, I know that from Little's law, the expected number of jobs in the system equals the arrival rate to the system, or the throughput of the system, times the expected response time. So what if we apply Little's law to this particular expression here in the numerator? Well, let's see what happens. This equals 1 over mu I plus, something over mu I. Well, this is going to be the arrival rate to that node plus the response time, or sorry, not plus the response time, times the expected response time. So it's going to be the expected response time to node I, but here's the thing. It's going to be n minus 1. Remember, it sees it with 1 fewer job in the system. Okay, times the arrival rate. Well, what's the arrival rate? Well, we have a notation or denotation for that. That just equals lambda I. And again, when there's n minus 1 jobs in the system. Well, I mean, what's our goal here? We're trying to derive an expression for Rin based off of Rin minus 1. We're trying to build a recursion, right? Because if we have that and we have our base case, we can just build up or build down, however you want to implement it. So we're almost there, but I mean, how in the world do we get this? Well, I'm going to rewrite this, one last time, just one more simplification. It's not going to quite bring us there, but it's going to allow us to maybe think about our next step. Well, what does this equal? Well, we know what this equals from over here. This is just going to equal pi times lambda I, we drop it because this is just going to be the total arrival rate to the system now. Drop that I subscript, n minus 1. Okay, times the rest. Over Ui. All right, fair enough. But have I really bought myself anything yet? Not quite yet. So I'm going to keep this example on the board, and I'm going to erase this over here. What's nice about YouTube is you can just rewind the video if you want to see this, so I don't have to worry about you guys, catching up with your notes. Okay, so if I can solve lambda n minus 1 based off of, potentially even these values, I'm good to go. But can I? Is there something else I can come up with? Another equation I can note. Well, again, I'm going to use Little's law. And I know the sum of all of these values as well. Think about this. What does this equal? Well, this is the expected number of jobs at node I when there's n jobs in the system. So you might think of it, if there's 3 nodes, the expected number at node 1 plus the expected number at node 2 plus the expected number at node 3 when there's n jobs in the system. Well, I know that there's n jobs in the system, so the sum of all the expectations has to sum up to n. Okay, but I can also rewrite this as something else. Again, from Little's law. So I know this equals n, but I know this also equals, so I'm just going to say n, and I'm just going to rewrite this as something else. From Little's law, I know this equals the arrival rate times the response time. Okay. I don't know why I put a capital N there. And usually I'm pretty good at giving lectures without, looking at my notes. Forgive me if I have to do it for this one. Like, you can see the equations start to get a little bit complicated, but we can just logic this out, knowing my base formulas. Okay. Times the response time, expected response time. Okay, that makes sense. Then n equals, and I'm just going to rewrite this. How am I going to rewrite this? Well, basically use the exact same observation from over here. Well, this equals pi times lambda n times lambda I. Sorry, same mistake. This is the total arrival rate to the system times the expected response time. Okay, look at this. Doesn't depend on I. What does that mean? I can rip that sucker out of the sum. So if I bring it outside the sum and I take all of this, divide n by that, I get an expression for pi, why am I calling these lambdas pi's, man? It's crazy. Just one of those days, For lambda n. And again, this should be brackets from that like that. It's not lambda to the power n, it's lambda n, like a notation. If there's n jobs circulating through the system. So of course this implies that lambda n equals n over some pi like so. Well, that's for general n. So check this out. Well, of course, that's going to imply, and I'll just write in n minus 1 instead of n here. So this equals n minus 1 over the sum. And I'm playing it a little bit fast and loose with these sums here, but basically this is from I equals 1 to what? To k. Right? We're just doing it for every node. So for every value of I here. So if we have a 3-node system, it's I equals 1, 2, and 3. It's a finite sum. And that's good news for us, because if it's a finite sum, that means we can solve it, or at least solve it using a computer exactly. Okay. To k pi, the expected response time, n minus 1 at I. Huh. So can we solve it? So remember, what was our goal? We wanted an expression for the expected response time of node I, given that there's n jobs circulating through the system, in terms of the response time of that node, given there's n minus 1 jobs circulating through the system. That's how recursion works. I don't need to tell you guys how recursion works. You're fourth-year computer scientists. So assume we know all these values. Assume we know Ri n minus 1 for all I. Well, if I know all those values, then I can solve this value using those values. Well, that means I have a total expression and a recursion for the expected response time, given that there's n jobs circulating through the system, for the ith node. So it actually works out. And just to take you through the actual process of this, and don't worry if you're not completely convinced yet, we'll actually do an example based off this node, based off this network. But here's generally how it's going to work. So solve base case. So we solve base case and we get the RIs for n minus 1. In this case, n minus 1 would equal what? Well, n equals, well, it's the base case. So we get it for n minus 1 equal to 1. I don't need to write that in. Okay. Once we have this value, what do we solve? Or these values, we solve lambda at n minus 1. Okay. Well, how do we solve lambda at n minus 1? Well, remember, we have all of these. It may be the base case, or it may not. But we have all these values. We can solve all these values. Remember, from the network, we can also get the probability values. Okay, so once we have the probabilities, once we have our n minus 1 at I, we can get lambda at n minus 1. Okay, sweet. Once we have this and we have this, that means from this equation over here, we can get the expected value of Ri at n. Okay, sweet. What do we do next? Increment n plus plus. Now these become the old values, and we just keep going. How far do we go? Well, remember, we're looking for maybe whatever, if we have 20 jobs circulating through the system, 5 jobs circulating through the system, whenever we get up to n equals 20, 5, whatever we're looking for, that's when we stop. So repeat until our goal, call that capital N, equals lowercase n. So what's the runtime? What's the complexity of this? Well, we have to do this cycle capital N times, because that's what we're really after. We want to know what's the expected response time, what's the expected number of jobs of each node, what's the utilization of each node when I have N jobs, capital N jobs, circulating through the system. Well, I have to do this circle N times. What's the complexity of doing this circle? Well, I have to solve basically k values. And what k values do I need to solve? I need to solve the response time for each node. And you can see this in the sum. The sum goes from I to k. So each cycle of the circle takes big OK time. I need to do it capital N times. So the overall complexity is nk. But hey, that's not too bad. Remember, before, our other two methods were combinatorial. This one is polynomial in the number of nodes and the number of jobs circulating through the system. So it's much more reasonable to calculate this using a computer, or even by hand for small values. And you'll recall, if you've taken a look at the assignment, the second part of the second question asks you to find some values for capital N equals 20. And some of you have been asking, that seems pretty crazy to do with the way we learned in class. That was true up until now, because you just saw this way. I would recommend using mean value analysis to tackle that portion of the problem. Okay, so given all of this, let's try and solve, and I'll do my best to erase all the derivations, but leave the equations up here so I can use them. Let's try to solve this network for maybe n equals 3, capital N equals 3. So this is my first equation. Like so, block that off. That's my second equation, and I got my base case up here. So everything should theoretically work out. Okay, and I have my p-values. So right off the bat, I can do the base case. And I guess I have to give you guys some mu values in order to do the base case. Let's say, so these are 3 nodes. Let's say mu1 equals, and the mu's will be given to you. Mu1 equals 2, and I'll say mu2 equals mu3, which equals 1. Keep the values relatively simple. Okay, so what does that mean? What's the base case? Pretty easy. The expected response time of the first node when there's 1 job circulating through the system, the expected response time of the second node when there's 1 job circulating through the system, and I guess I'll say it out loud, expected response time of the third node when there's 1 job circulating through the system. Well, that's of course going to be 0.5, 1, and 1. How do I get those values? Well, it's just 1 over mu I. What units are these in? Whatever unit you're measuring. You could think of these being as, this is seconds and this is rates, so 1 over seconds. But it doesn't matter. We could be measuring time in nanoseconds, microseconds, hours, years, millennia. It doesn't matter. What's next? Well, now that I have these R values, that's my base case. Now I solve lambda pi n minus 1. So this is R n minus 1. So I need to solve lambda 1. So lambda 1 equals what? Well, it's going to be n minus 1 in the numerator. Remember, right now n minus 1 equals 1. So it's going to be 1 over something. And it's the sum of the response times these probabilities. Remember, these probabilities over here, we can just get from the network itself, from the structure, from the dynamics of the network. So P1 times R1, that's going to be 0.25 plus 0.15 plus 0.35 So this equals 1 over 0.75. Some of you can do that in your heads, I'm sure, and if I did it as a fraction, might have had a better chance at it. Did I write it down in my notes? I'm out of frame here, probably. So, based off my notes, something like that. 1.33 repeating. Okay, I'm gonna erase this network. You know what the network looks like. Well, now that I have that value, I can calculate my response times when there's 2 jobs circulating through the system. So maybe I'll just look at a specific example here, a specific node I mean. So I'm going to do it when there's 2 jobs circulating through the system at node 1. Okay, well this equals 1 over mu I, so that's going to be 0.5 plus, now I get probability of P1 times lambda n minus 1, but I have that over here. I wrote lambda 1, what I should have wrote was lambda 1 up top, like so. So what does that equal? So 0.5 times that? Oh man, I don't know. It's in my notes. I don't think it is. So I'm gonna have to leave this as an exercise for yourselves. But it's gonna be something like 0.5 times 1.33 times 0.5 over 2. So where am I getting these values? This one is P1, this one is lambda 1, this one is the response time, and this one is mu1. And that's how I got that. And similarly, you can calculate the expected response time of this. So this is the expected response time of the second node, given there's exactly 2 jobs circulating through the system. And of course, you can get the response time of the third node, given that there's 2 jobs circulating through the system. And double check my math, but I think this one equals 1.2, and this one equals 1.47. And if I can read my messy writing, I think this equals over here 0.67. The numbers look like they could be right, but again, double check these for me. Very easy to make mistakes with this type of stuff. Okay, now what do I do? Remember, I'm doing this for n equals 3, capital N equals 3. So I want to know the values when there's 3 jobs circulating through the system. So these are the values when there's 2 jobs. I mean, I'm not done yet. I need to get this superscript value up to 3. Okay. What's up? What do I do next? Come back to the circle. Now I have to solve for lambda. I just solved for, r at n minus 1 here. Now I have to solve for lambda. So I need to solve for lambda at 3. Or sorry, lambda, my mistake. Lambda at 2. So I need to know the arrival rate when there's 2 jobs circulating through the system. Well, what's that? Check it out. Right here. So I know this is going to be 2 over, then I sum all of these up. So it's going to be 0.5, that's P1, times this, 0.67, plus P2, that's 0.15, times 1.2. Again, double check my math here, but you get the general idea how you would solve these things. And then last one, 0.35 times 1.47, plus 0.35 times 1.47 0.47. And we'll just extend that, make it look nice. Okay, what does that equal? Do some quick math, check your notes. 1.94 maybe? Could be. Double check my math. Good exercise for you guys. Okay, now that I have that, what's my last step? Well, I'm after the expected response time of all three of these nodes when there's exactly 3 jobs circulating through this system. Well, I basically just completed this step. Now I do this step. So I'm looking for the expected response time of R1 when there's 3 jobs circulating, and the same for the other 2 nodes. How do I solve that? Boom, got the equation right here. Crunch the numbers, check your notes. 0.82, 1.35, and 2 precisely. So first of all, do these numbers make sense? Well, it makes sense that the response time at the first node is the lowest because it has the highest processing rate. And if you go back and you check the network, it was more likely for a job to get routed to the 3rd node than it was the 2nd node. So it makes sense that this one has a high value as opposed to these 2. So the ordering does make sense, but again, it's always nice to have a second set of eyes on the numbers. So just, check the numbers yourself. It should all line up, but let me know if it doesn't. Okay, so what did I say at the beginning of this mean value analysis? What things could we get from it? Well, we could get the expected response time, and we could get 2 more things. We could get the expected number of jobs at each node, and we could get the utilization at each node. Well, this is how we get the expected response time. How in the world would we get the expected number of jobs at each node and the utilization? Well, that's pretty easy. If you understand what we've done so far, you should be able to figure this out. So, given I have values available to me, that full mean value analysis framework, how do I determine the expected number of jobs at node I? And how do I determine the utilization of node I when there's n jobs circulating? Let's think about that. Pause the video actually and think about it yourself. Maybe 3-5 minutes. See if you can come up with it. Pause. We're back. Well, this is just an application of Little's law. We actually use this in the derivation of all these terms, but we know that this is just going to equal lambda I, the arrival rate to node I when there's n jobs in the system, times the response time, expected response time of node I when there's n jobs in the system. Well, how do we get this? Well, again, this is just going to equal the probability I times the arrival rate to the system with n. And we're running out of space. We can handle it. Just get smaller and smaller. Easy. Fit it on. Okay. This term over here is just this term as well. So that's how you get that. How do you get the utilization? Remember, the utilization is the probability that there's more than one job, or more than 0 jobs, I should say, 1 or more jobs at a particular node. And we had a couple, well, since the beginning of this course, the way you can think about that is it's the arrival rate over the processing rate, lambda over mu. Well, what's our lambda here? Lambda I n over ui. Okay, well, what's this? Very similar to up here. It's just going to be pi times lambda n over mu I. And just, I guess that should be consistent. I did write a capital N in this superscript here. Whew. I'll just write lowercase. And that's mean value analysis. So it's a little mathy, it's a little bit of a grind, but honestly, it's easy marks. Once you understand it, it's just like these couple formulae here. You just put it in, you start turning the gears, right? Okay, I did this step, just do it one more time. You just keep repeating this. And if you have big values of capital N, right, and someone's asking you a question on an assignment, implement it on like, Python or Java or MATLAB or whatever you want. So that's what I would suggest doing. If you have any questions, of course, you can always post it to Piazza. For tutorial problems, there'll be a little bit more information to come. Otherwise, thank you very much for your attention, and I'll catch you in the next lecture.